Hello, everyone. My name is David Chester, and today I'm going to present a talk that I gave to Louis Kauffman's quantum topology seminar on March 24th to the University of Illinois at Chicago. The title is The Universe as a Holographic Quasicrystalline Tensor Network. Just a bit about myself. I received my undergraduate at MIT studying particle physics and quantum field theory, and I did my thesis on electromagnetic scattering. From there, I went on to do a PhD at UCLA where I looked at QCD scattering amplitudes. And then I started studying this method called the double copy, which looks to find gravitational solutions from Yang-Mills theory, or QCD. From there, I was actually able to show that you can use gluon Feynman diagrams as well as graviton Feynman diagrams to get at gravitational radiation through the double copy, which allows for scattering methods to be applied to radiation. Since I've been at QGR for the past 2 or 3 years, I've been interested in many topics, but a few of my favorites include a notion of elastic quasicrystals that are dual to gauge theories, and I'm interested in discrete and continuous formulations of metric affine gravity. I also have an intense passion for standard model and how that might fit in with gauge gravity, especially in relation to E8. For this talk, I'm going to start by just introducing a simple Hamiltonian for 5 maximally entangled qubits. We'll study this system and show how the ground state leads to a notion of topological error correction with universal quantum computation. From here, we'll be looking at these tensor networks on hyperbolic honeycombs, and we'll look to calculate the code rate of these codes, which is essentially the efficiency. From here, we'll introduce briefly the notion of an E8 Hamming code and discuss the notion of a quantum Hamming code, which motivates us to generalize ourselves from quantum mechanics and work towards quantum field theory stemming from E8 gauge symmetry. In this pattern, we'll be interested in looking at qubits in quantum mechanics and generalize these to relativistic spinor fields. From here, generalizing the Lorentz group to the conformal group makes contact with twistors, and we can enlarge the conformal group to a quasi-conformal symmetry to make contact with a notion of pseudo-twistors. From here, this will motivate a notion of H4 as the Elser-Sloan quasicrystal that stems from E8, which motivates a notion of a holographic quasi-conformal quasicrystal. From here, we'll look at the ADE classification and try to shed light on how H4 relates to a secret duality between D4 for space-time and membranes, while the A4 will be related to gut unification of the standard model. The basic idea is it seems like H4 is this quasicrystal that is in between these two crystals in some sense. Then we'll discuss some gravitational symmetries for 3 generations of the standard model and go a little bit beyond E8 to discuss the Golay code, the Leech lattice, and briefly mention notions of M theory, generalizations from there, including A theory, monstrous M theory, and recent work that discussed applications for warm dark matter stemming from the Leech lattice. Since this talk was for quantum topologists, I figured I would just briefly start by mentioning that we're interested in topological spaces with tensor products. And one of the main applications of this study includes topological quantum field theory, as well as the study of condensed matter phases, including the fractional quantum Hall effect, string net condensates, quantum liquids, as well as many other exotic phases of matter. But today, we're going to be more focused on the applications of topological entanglement for tensor networks of qubits. Now, we're interested in understanding how to make fault-tolerant quantum computation. And one of the main questions we're interested in at first is, what are the best networks for encoding topological quantum error correction? We'll focus on hyperbolic tilings of qubits and introduce a notion of discrete holography. So to introduce what qubits are to start, you can have this wave function psi that is just a simple 2-dimensional complex vector. But since we don't care about how the state is normalized, we want the total probability sum to 1, we can say that the spinor is in this complex projective line. So CP1 is the complex projective line. So we have this projective space where the qubit is living, and the qubit has 2 eigenstates. So if you take the poly Z operator, which is a simple 2x2 identity matrix, it's a simple 2x2 matrix, right? When it acts on this state, it has 2 eigenvalues of plus or minus. And from there, this allows us to get into quantum computation, as we can use Z, X, and Y polymatrices to do arbitrary SU2 qubit rotations. And the basic idea is that if you have a classical bit, you can have 0 and 1. And those states, that's kind of the computer stance on it, but you can also look at it from the spin perspective. So you could have plus or minus or 0 and 1, it's the same thing here. But the qubit, the quantum bit, actually allows for superposition states. So there's more than just the 0 and 1, we can now have something that is in between. Once we have this in quantum mechanics, we can then take a tensor product of qubits to get a network of qubits. And then we can get into quantum computation that is acting on this network of qubits. So in order to have universal quantum computation, as I was alluding to, we're going to want this arbitrary SU2 qubit rotation, as well as this C0 gate operation, which is going to allow us to entangle or disentangle two different qubits so that we can understand how the entanglement structure of the qubit network is behaving. So as you might have heard, quantum computers have the decoherence problem, which basically means that quantum measurements destroy quantum states. And since information is leaking out in various different ways, any thermal noise will lead to a prepared quantum state to decohere, which destroys the quantum computation. Now, one solution to this is to go to topological quantum computation. What we're looking to do here is to entangle states and encode quantum information in the topological configuration of the qubits. And the reason why we want to do that is such that if we measure the topological state in a way where we don't measure any information about a single qubit, if we do so in the appropriate manner, then even if a single qubit decoheres, we can understand from the entanglement state what the quantum information that we're interested in is actually encoding. And in order to do that, we're going to need a few ingredients, including a twofold degenerate ground state. That's at least one way to implement this that we'll discuss today. And the basic idea is that the twofold degeneracy of this ground state admits operators that mathematically behave like the SU2 operators on single qubits, despite the fact that this ground state is actually a combination of qubits. So underneath it all, we'll have these physical qubits, but then we're going to entangle them such that they're maximally entangled. And then from there, we will understand how to find an emergent logical qubit from a collection of physical qubits. This allows for the logical qubits to have error protection and in cases also error correction. But the trade-off is that now we need more qubits for the same amount of computation, because we're going to need many physical qubits for a single logical qubit. However, there's a lot of interesting physics here, because we can think about a polytope and in 2 dimensions, and we can put qubits on the edges and think of that as being the boundary. What we'll find in these holographic tensor networks that we'll be looking at is that the logical qubit can be associated with the bulk. It's sort of emergent from the combination of the boundary, which is naturally ascribed to the bulk. And this has a lot of motifs that parallel nicely with ADS CFT and holography. So this gives us a toy model or a discretization of the ADS CFT correspondence. So to get into this a little more, we're going to need to discuss stabilizer codes. And this is originally coming from classical code theory rather than quantum theory. But if we have self-dual classical codes, we can then repurpose these classical codes to make quantum codes. Once we have the quantum codes, we want these SU2 poly operators, including the identity matrix, as well as the 3 poly matrices, to allow for rotations of our qubits. The idea is that any errors that we want to detect or correct we're assuming that these errors are a subset of the SU2 rotations. So if we have access to these qubits, we can understand, if we have access to these operators and we see that something goes wrong, we understand how to fix them. And it's actually going to work even more slick than that, as we'll see. But the basic idea is you can have an n, k stabilizer code, which encodes k logical qubits into n physical qubits. And we can define the code rate as being the ratio. The basic idea is that we're going to have multiple physical qubits for fewer logical qubits. So this code rate is going to be some fraction or some percentage. So the idea is that the more efficient topological code would have a higher code rate, as we would be able to get more quantum computation for less physical qubits, because we will be using the logical qubits for the computation. So we can use these abelian stabilizer subgroups, which involves a tensor product of these qubits. And from here, if you look at n minus k, that will give the number of generators that is in the stabilizer subgroup. Now, one type of topological error-correcting code includes this toric code, which is simple and very elegant, but it has some scalability issues. The nice thing about it is that you can use a very small patch of a lattice and have periodic boundary conditions. So you have this toroidal geometry, and you can use these different operators to get notions of logical qubits. However, if you actually tried to build a quantum computer with this code, the problem is that if you scaled up the lattice to being larger and larger, you would only get 1 or 2 logical qubits for the entire lattice. Therefore, you wouldn't actually be able to do any realistic quantum computation, as you would need multiple qubits to implement any useful computation. And it's actually understood from the literature that 5 is the minimal number of entangled qubits for a single error-correcting code that is fault-tolerant. And keep this number 5 in mind, as it will be an important motif for the second half of the talk, which introduces notions of 5-fold symmetry associated with quasicrystals. So a few years ago, Postovsky, Rashida, Harlow, and Preskill introduced this, what's now called the happy code, due to a concatenation of their letters. And the basic idea is we can take a hyperbolic tiling, such as the 5-4 hyperbolic tiling shown here, and we can put qubits on the edges. And if you do this for the entire lattice, you can ask about how many logical qubits there would be given the number of physical qubits. And so the interesting question to think about is, what is this code rate? How many logical qubits will I get? What is the ratio of logical qubits to physical qubits as I scale up and increase the number of physical qubits? What they found is that in order to scale up the system to the infinite limit, you can do it step by step using this simple inflation rule. And the way they depicted it in their paper was using a diagram like this, but it became difficult to understand how to generate these diagrams from scratch. These pictures on the right are pictures that I created just to visualize it a little more clearly in relation to the hyperbolic tiling. So we can study their stabilizer code by just starting off with a very simple example. Rather than going to the infinite limit of going out shell by shell and considering the whole lattice, we can start by considering a simple pentagon of the lattice. The basic idea is we're going to take 5 qubits and place them on the edges of a pentagon. From here, we can look at this stabilizer code, which combines these 5 entangled states. And then from here, you get these 5 different operators that include tensor products of the different Pauli matrices. Now, the remarkable thing about this code is that these 4 operators are all permutations of each other. So we have x, z, z, x, I, and you notice that S2 just takes this I, this identity matrix, brings it around front, and then we have the same pattern of x, z, z, x. Not only are S5 all permutations, but the remarkable property is that S1 times S2 times S3 times S4 also gives S5, which means that we could get access to all 5 of these operators simply by using only 4 alone. So the stabilizer code has this stabilizer subgroup with 4 generators. Now, what Noah Bray-Ali, one of our collaborators, realized is that you can take these operators and make a very simple Hamiltonian that gives a 32 by 32 matrix, since we are entangling 5 qubits and we have 2 to the 5, which gives 32. So when you take this Hamiltonian from these operators, you plug it in to Mathematica, you get the ground state, and you'll find that you get a 2-fold degenerate ground state, which we're going to label as psi1 with a plus or minus. And the plus or minus is suggested because you see that the ground state is encoded from these operators acting on the all plus or all minus states that is the tensor product of the boundary qubits. And what we're finding is that this ground state has this 2-fold degeneracy, which is exactly synonymous with the structure of the qubit itself. So when we study the ground state of these 5 entangled qubits at low energies, we can approximate it as simply being in this degenerate ground state, which is associated with the bulk. And that allows for operations, as we'll see, that mimic the operations of a single qubit. So if we take a single poly X matrix, and then we take the tensor product of all those together, we can get this X tilde operator. And if we do the same with Z, we can get the Z tilde operator. And when we act with these X and Z operators on the degenerate ground state, we find that it has the same operations as X would on a single qubit and as Z would on a single qubit. This allows us to claim that this ground state is a notion of a logical qubit, as now we have access to the same type of manipulations mathematically that we did on a single qubit. Now, so for this example, the code rate is fairly simple because we just want to look at the ratio of the number of logical qubits to physical qubits. So here we have a single logical qubit in the bulk of this pentagon, and we have 5 physical qubits on the boundary. That gives us 1/5 or 20%. Then another observation that was found in the literature comes from Boyle, Dickens, and Flicker. What they realized is that these hyperbolic tilings allow for a quasicrystal to be found on the boundary, suggesting that there is some quasicrystalline discrete CFT that is on the boundary of these discrete hyperbolic honeycombs. Now, what we see here is that they had a couple different lettering and numbering schemes to try to encode what is on the boundary. It can take a little time to figure out precisely how these things are derived, and it also wasn't precisely clear what the scheme was computing. So what we did was to first take their code, understand how it works in the 5-4 hyperbolic tiling, and then we actually modified it to get a new code such that we could actually use that code to efficiently compute the code rate of the entire network to find the same result of the happy code rate. And what we found is that the Fibonacci chain is found on the boundary in a precisely similar way, but at a larger scale than the Fibonacci chain found previously. So what we see here, rather than using their method of having these A's and B's, which is based on the types of edges, it's a little complicated to figure out how they're assigning the A and B. Our scheme is a little simpler. You simply look at the tile type and you count out layer by layer and you say, how many external edges does this tile have to the next layer? It can only be a finite number because we're dealing with a polytope. So in this case, we have 2 cases. In this network, we're going to have this alpha character, which denotes a pentagon that has 4 external edges, or we're going to have this beta character, which is a pentagon with 3 external edges. So this one right here is a beta because at the next layer, it only has 3. So from here, if you look at the inflation growth of alpha and beta, not only do we find that there's a substitution rule to take the original quasicrystal code and turn it into this lettering scheme, we also find that the inflation rule of this new letter system is found from the Fibonacci chain inflation rule applied twice, which gives the same growth matrix that was used in the happy code. So now we can see how we can use this quasicrystalline inflation rule on the boundary of this discrete hologram and use it to calculate the code rate of these holographic tensor networks. And so we ended up looking at a wide number of different tensor networks and figured out how to calculate what the code rate was for all of these different networks. So moving on from here, we can then introduce the classical Hammond code and discuss its relationship to E8. The Hammond code, there's many different Hammond codes, but the 7-4 Hammond code is an error correcting code. It takes 4 bits of data and it expresses them in 7 bits, such that 3 of those bits are recomputed from the original data to give certain parity checks. Now, when all of the 7 bits are transferred, they're sent down some signal line, you can look at those parity bits and check the output of those to see if it makes sense given the information in the other 4 bits. This can be used to detect an error. And the remarkable thing is that for the Hammond code, you can even implement the parity checks in such a way that reading out the parity check actually determines the location of the error. And what actually occurs here is the Hammond code can it can detect a single error, but it can also correct it. You can extend the Hammond code from there to this 8-4 Hammond code, which has 8-bit integers, and that can detect a second error. This ends up being related to what is known as a doubly even binary self-dual code. Now, if you don't understand all this terminology, that's fine, but the basic idea is that it is understood that these types of codes relate to self-dual lattices. And in this case, this Hammond code relates to the E8 lattice. And the fact that this is a doubly even binary self-dual code relates to the fact that the E8 lattice is self-dual. From here, as I was mentioning before, you can combine two classical codes to get a quantum code. So in this case, you can have these stabilizer codes, as I was mentioning, including the Steen code as one example. And here, the way you can think about it is there's different types of errors that can occur. One is the bit flip error, which is a classical error. But now that we have this qubit, there's also this phase information that tells us information about superposition. And so we can have phase flip errors as well. So if we take two classical Hammond codes, one for this bit flip error and the other for the phase flip error, we can combine them such that we have a quantum Hammond code. So we have information for error correction for qubits. And it's also interesting to note that this has been realized in M theory, in particular for an octonionic realization of M theory with octonionic superpotentials. The basic idea is that M theory is giving us a cosmological model that is suggesting that the universe is a type of error correcting code. Okay, given all this information, it's now clear that quasicrystals seem to be connected to holography and these error correcting codes. And some guidance that we've gotten from Clea Irwin here for us at QGR is that we want to understand the relationship of geometry and algebra so we can derive new quasicrystalline algebras that are necessary for what we're after here. And the basic idea is that there are these Lie algebras that are useful for Lorentz symmetry in gravity as well as gauge symmetry in the standard model. And it is understood that the geometric classification what is understood is that the classification of these algebras is described by a geometric classification. So there is this Cartan-Killing classification that specifies what all of the simple Lie algebras are in terms of geometric counterparts. It is also understood that these root polytopes corresponding to generators of these Lie algebras lead to a lattice, a root lattice. And when you take these root lattices, the vertices of the lattice, you can apply this cut and project method, and that gives us access to quasicrystals. For instance, the Elser-Sloan quasicrystal can be found from E8. And that is so we're projecting from an 8-dimensional crystal and then obtaining a 4-dimensional quasicrystal. However, at this point in time, there is this notion of what I should call quasicrystal Lie algebras, but no one has yet found the Elser-Sloan quasicrystal Lie algebra. So in order to complete the vision that we're interested in, we might want to look further into understanding what types of quasicrystal Lie algebras are out there. So we can understand the correspondence between geometry and algebra for quasicrystals, and then use this geometry to see if it relates in any way to the Lie algebras that are associated with gravity in the standard model. We've also done some work related to this concept called the self-simulation hypothesis. The underpinning of this is we basically want to use a code theoretic language with symbols and syntax. The reason why we want to look at quasicrystals is because they're inherently code theoretic. The way I like to think about this is if you have a square lattice and you specify a single square, that square will determine uniquely the position of all of the other squares in the lattice. So there's a lot of structure, but there's no freedom, there's no syntax, there's no language. On the other extreme, we could have a completely random tiling. There's no order, there's no structure, there's no syntax, but there's immense freedom. With quasicrystals, something different and in between occurs. You get a little bit of both. If you take let's say a Penrose tiling, you have these darts and kites. If you take a kite, you put that tile down, that will uniquely determine the location of some of the other tiles in the quasicrystal, but there will actually be multiple quasicrystalline tilings that can be allowed. That gives us a notion of freedom, yet there's still syntax as there's still structure. There's still order in the quasicrystal that is not inherently random. So in this sense, we're motivating the idea that quasicrystals could allow for a code theoretic language that leads to pre-physical information that leads to some sort of emergent space-time code. And the idea is that there will be different strata of information, including physical information using self-referential symbols and conscious information related to non-self-referential symbols. But for the rest of the talk, we're just going to talk about physical information and suggest some ideas for how to tap into what this code theoretic language might look like, at least for the physical information. So the lesson of the first half of the talk was that 5 physical qubits lead to a single logical qubit. The idea I'd like to share with you now is, think about this. What if our physical world is actually encoded in the logical qubits? In other words, what we view and observe as physical could really just be abstract logical information, whereas the true physical real world is actually these deeper physical qubits, such that in the previous story, the physical qubits lead to logical qubits, but as we observe reality, we see the information encoded in these logical qubits, and we think those are what is physical. In this sense, if we think of these quantum fields as emergent logical spinors, then we get this idea that there's this pre-physical code of physical spinor fields, and these lead to the logical spinor fields, which are currently what we call physical. Now, the idea is we want to think about qubits and their symmetry, which was related to SU2, and then we realized that this was related to spin 3, which is the double cover of SO3, so 3-dimensional rotations. When we go from, when we introduce relativity, since quantum mechanics is non-relativistic, the basic idea that we learned from Einstein is to unify time with space. So once we have relativistic quantum mechanics or quantum field theory, we want to work with the Lorentz group, which leads to a notion of SL2C spinors. However, we can go further and look at the conformal group, which adds a light cone to the 3 space and 1 time dimensions, giving spin 4-2, which is isomorphic to SU22. And this SU22 acts on twistors, which are similar to massless Dirac spinors. I'll also point out that you can get different notions of pseudo twistors, which are essentially twistors of different signature, including spin 3,3 and spin 4,4. And in the literature, it's been pointed out that spin 4,4 can be utilized as a quasi-conformal symmetry due to work from Gneiden. And also, Kostant pointed out that spin 4,4 can be used potentially for 3 generations of matter, but he came from a mathematical perspective. There's also work discussing the role of spin 4,4 for double field theory, which relates to phase space and the notion of T-duality in string theory. And work that I'm currently involved in with Xerxes Arsiwala at the Wolfram Institute, as well as Lou Kauffman, we're currently looking at aspects of phase space in various formulations of gravity, which makes contact to this notion of spin 4,4. We can also get even higher pseudo-twistors, such as spin 12,4. And these spinors will be important for us because they're coming from a particular non-compact real form of E8 that will become interesting for in later slides, as you'll see. So going back to the classification of Lie algebras in terms of the geometry, there are these different root systems that correspond to each Lie algebra. For instance, if you have the AN root lattice, that ends up corresponding to the SUn+1 Lie algebra, which also corresponds to the SUn+1 Lie group. Here, we depict all the different 2-dimensional root systems that you can have. So you have A2 with this hexagonal symmetry, and there's also B2, which corresponds to SO5. We also see that it makes sense that SO4 is contained within SO5, and we see through the root polytope geometry that the roots of D2 are contained within B2. So there's some self-consistency. It's also a fact that G2 contains SU3 or A2, and we can see the hexagonal structure here in G2 as well. So when we classify these Lie algebras, what we find is that there are these 4 infinite classes. There are these ANs for integer n, the BNs, the CNs, which relate to symplectic groups, and the DNs, which relate to even special orthogonal groups. However, there are 5 exceptional Lie groups that don't fit into any infinite pattern. And so for this reason, they're called exceptional because they stand out. Now, to motivate the physics from this mathematics of exceptional groups, it's really curious to pinpoint the E series, as E2 corresponds to A2, which is the symmetry of SU3 used for QCD. Now, if you were to take the standard model, that would be SU3 cross SU2 cross U1, but the root polytope of U1 is really 0-dimensional, so there's no root system there. And so you would get SU3 cross SU2 leading to A2 plus A1. And actually, that is what E3 is. Furthermore, the first introduced grand unified theory that unifies the standard model gauge group into a single group is SU5. That corresponds to A4, which is what E4 is. Finally, D5 corresponds to spin 10, and it's known that spin 10 unifies all the fermions of a single generation of the standard model into a single spinor representation of spin 10, which remarkably is the same as E5. Finally, E6 is something new, E7 is something new, and E8 is something new. So it's curious to explore E6, E7, and finally E8 to see if we can get more than a single generation of the standard model. Now, if we go back to the standard model, we have this SU3 cross SU2 cross U1 gauge group, as I mentioned. And so each simple Lie algebra here corresponds to a set of vector bosons. And I depict the kinetic terms for the Lagrangians here, which also encodes their self-interactions. So now we can look at E8 and understand how SU5, SU10, and also this Petit-Salam gut model, the SU4 cross SU2 cross SU2, all fit together. It's been well known for quite some time that SU5 fits in SO10, and I should also mention there's this flipped SU5 that adds an additional U1 that also fits in SO10. It's also understood that the Petit-Salam gut model can be derived from SO10, and these can both be broken here, which eventually leads to the standard model here. Now, the electroweak symmetry breaking eventually shows that the weak force combined with the weak hypercharge can break to the electric charge. Finally, we can look at SO10 and go further. We can embed SO10 in E6, which is embedded in E7. So we can get to SO10 through E7 and through E6, or we can also follow another path from E8 that looks at E6 and gets an SU3. That's been used by Bars and Gunani to try to make contact with 3 generations of matter long ago, around 1980. But that hasn't been followed up too much. So here at the bottom, I just depict the SO10 representations, break them to SU5 cross U1, and then further here. So you can see various different quarks right here and leptons here. And furthermore, here are gluons. There are W bosons here, and you can use these for the weak hypercharge. These are all fitting into SO10, single SO10 representations for the fermions and the bosons. And the basic idea is that these exceptional groups include spinor representations. So we're curious to see if these exceptional groups can combine or unify the state space of the fermions and bosons. So the first question you could ask is, well, is it possible for E8 to encode 3 generations of the standard model for some quantum theory? In order to do that, you would typically think you need 192 off-shell degrees of freedom. Now, the basic idea is you can have a Dirac spinor, and a Dirac spinor you can think of as an electron with minus charge, but there's also this positron in the Dirac spinor, which has the plus charge. And there's also the left and right spin states of both the electron and the positron. These correspond to the classical degrees of freedom of the Dirac spinor, which is 4. But the quantum degrees of freedom gets multiplied by 2. So the Dirac spinor has 8 off-shell or quantum or virtual degrees of freedom. So if we looked at an electron, a muon, and a tau as 3 Dirac spinors, we would think we need 24 degrees of freedom. There's also quarks and other leptons, such as the neutrinos. So when you take this 24 and you combine it with all the other different charge types, that's what gets you to this factor of 192. What we were able to observe is that if you study the structure of spinors coming from spin 3,3, you can combine irreducible representation of spin 3,3 to get a 16-component spinor that efficiently encodes 3 on-shell degrees of freedom associated with 3 different Dirac spinors, because you can think about there being 3 different spin 3, 1s that are embedded inside of spin 3, 3. What this allows us to do is to get a new enhanced gravitational symmetry using spin 3, 3 that efficiently encodes the spinors. The caveat here is that we get this efficiency where we can use 16 degrees of freedom for the price of 24, but we can only do this if all of the 3 generations have precisely the same charges, which is what we find for the electron, the neon, and the tau. They all have the same charge. Therefore, we can fit the 3 on-shell states of the electron, neon, and tau into a single 16-dimensional spinor. Now, when we run through the numbers again and add in the neutrinos as well as the quarks, we realize that if we use these spin 3, 3 spinors, what we can obtain is 3 off-shell generations of the standard model in a single 128 spinor rather than a 192 spinor. Now, this is something that has been largely overlooked by Gerrit-Lisi. He didn't precisely understand the details here, and also Distler and Garibaldi, in their refutation of Gerrit-Lisi's model, they specifically stated that if you use spin 3, 1 to get 3 generations of the standard model, it doesn't work. However, that does not rule out the possibility that E8 can be utilized, as we see here, as there are other gravitational symmetries that are enhanced that allow for a more efficient encoding of the spinors. So Gerrit-Lisi actually inspired us. He had this paper in 2015 where he looked at spin 12, 4, and then he broke that to spin 4, 4 across spin 8. Now, if you look at the representations here, stemming from the 248 dimensional representation of E8, you get spin 4, 4, which has 28 dimensions here, and then spin 8, which has 28 dimensions here, and then you get these representations. Since you get these 8 vector representations here, that leads to 192 degrees of freedom right here, which is very tempting to associate that with this 192 right there. However, if you follow the mathematics, it is very clear that these 8 vectors are vector representations, not spinor representations, so they're not fermions. So they're bosons. Therefore, as we were describing, E8 only has 128 spinors, whereas it was not exactly clear what Gerrit-Lisi was proposing, but it seemed like he was suggesting that you might want to use these vector bosons for the fermions, which would not lead to the correct interactions. So the basic idea is that our observation about spin 3, 3 as a type of spinor, we can generalize that to spin 4, 4. Now, twistors are spinors of the conformal group, and the conformal group of spin 3, 3 is actually spin 4, 4. So we can understand that if we have spin 3, 3 twistors, those are actually equivalent to spin 4, 4 spinors. So this allows us to uplift our notion of spin 3, 3 from the previous slide and to repurpose some of Gerrit-Lisi's observations with a more rigorous understanding of the representation theory stemming from E8. We'll also point out that spin 4, 4 relates to the split octonions, while spin 8 relates to the octonions. Now, this is a little bit of a conjecture here, but string theory looks at different membranes that are complex, and they take this large N limit of these complex membranes, and so they end up stacking together an infinite number of D0 branes in certain cases. And when they do that, they have to go to this infinite limit, and that causes a lot of complications because infinity is a very large number. Now, the point is, if you go to octonionic geometry, there is no OP3, there is only OP2, which is related to the fact that the octonions are, in a sense, exceptional, which relates to the structure of the exceptional Lie groups themselves. Now, the basic idea is that in order to get efficient quantum gravity, scattering, and radiation, it helps to have what is known as a manifest color kinematics duality, which forces a trivalent graph representation. The basic idea is that if someone were to construct a network of octonionic D0 branes, you would find that they would have to be in this manifest trivalent graph representation, which might be suggestive for efficient quantum gravity. So the basic idea is we want to look at dualities within E8 to understand how to combine these insights stemming from the octonions and split octonions, yet make contact with grand unified theories such as SU5. Another problem is that it seems like we need supersymmetry, or at least that is one interpretation. Stephen Adler at one point around 2002 to 2004, he pointed out that maybe E8 is a superalgebra because it has these spinor representations. However, it is clear that it is not a superalgebra. Another property of superalgebras is that they have the same number of bosons and fermions. In some of the work that we were doing, what we realized is that if you look at the quotient space of E8 with SU32 cross SU5 for this particular non-compact form of E8, what we find is that there are 200 degrees of freedom here. When you compare these with spin 12,4, that helps identify what degrees of freedom are bosonic versus fermionic. What you find is that the 200 degrees of freedom here have 120 fermions, while E8 only has 120 bosons. What ends up happening is that 8 neutrinos in SU5 gut, the SU5 singlets get that if you interpret them as coming from E8, they get absorbed into this gravitational symmetry. What this is suggesting is that by looking at these structures and studying these dualities, it seems that E8 is hinting that the theory is naturally encoding 128 fermions, yet leading to a picture where there are 120 interacting fermions and 120 bosonic degrees of freedom. That makes it closer to supersymmetry, but still, E8 is not a superalgebra. However, Piero Turini recently realized that you can take a Grassmann envelope of E8 to convert it into a Lie superalgebra. And no one had really pointed this out before for E8, which was done fairly recently. So if we use the same trick, we can apply it instead of the compact form that Piero is interested in, we can apply it to this non-compact form and get access to gravitational symmetry associated with non-compact groups such as the conformal group and the Lorentz group. This allows us to use E8 and get a new superalgebra. And then we also have the motivation for why there might be supersymmetry based on the interactions that seem to be emerging from this picture. So now to just have a little fun, Gerrit Lisi is known for his surfing abilities, and it was stated that maybe he wiped out, but let's consider a string theorist that might be surfing. The basic idea is that superstring theory suggests that when you have fermions with supersymmetry, that we need to go to 10 dimensions of 9 space and 1 time. And then from there, M theory looks at 10 plus 1 dimensions. Throughout this whole story, it's been understood that the 3 plus 1 dimensions of spacetime should be some subgroup of this SO9-1 or SO10-1. Now, since I mentioned this non-compact real form of E8, this E8 minus 24, I'll just mention that the string theorists did briefly point out that in studies of 2-time M theory, if you look for a background independent description, it's natural to think of the 2 brane embedded in this total space of SO10 plus 2. So you have 10 plus 2 dimensions with this 2 brane embedded in there. It's actually helpful to think of the 2 brane as being a separate space, such that you separate that and combine them into this larger symmetry, SO12-4. And Martinek actually pointed out in a conference proceeding that this motivates that 2-time M theory suggests utility from E8 minus 24, this particular non-compact real form of E8 that I'll be discussing more. I'll also point out that Witten and collaborators have pointed out that E8 is a gauge theory. So this suggests some tension, as it's sometimes thought that there's this debate between Gerrit Lisi and string theorists, because Gerrit Lisi had this E8 theory, whereas string theory is saying that this E8 theory is wrong. However, it's clear from the literature that E8 is and has been used in string theory far long before Gerrit Lisi started working on this, which provides a little more context on the tension. However, from one perspective to take is that both there, no one has fully figured this out yet. So one perspective to take is that if you look at SO12-4, you can actually identify SO9-1 as having nothing to do with space-time, but rather actually being some type of internal charge space. Now, this was recently articulated in a conference by John Baez, but I want to point out that we posted a paper on the archive that already proposed a more explicit model for his conjecture that he did after what we suggested, which is stemming from E8. The basic idea is that one idea is to recover 3 dimensions of space and 1 of time from SO33, which is commuting with this SO9-1 such that you wouldn't find space-time in this SO91 space. I will point out, however, that this is just mathematics. So there are multiple SO91s that are in this SO12-4. So of course, there will be some SO91 that does contain space-time, and that perspective could be considered as well. So there's still a lot of math that can be explored, but what we're finding is that there's an opening of opportunity where it looks like two competing theories are actually, there's something good that is actually in between both of them. So we can learn from both parties rather than picking one or the other. Now, I'll also mention that Sirag introduced this notion of 8x theory, where the x really stands for this x factor behind this ADE classification. And one potential issue with this title of his 8x theory is the x didn't really stand for anything concrete. It was just his x factor. And here's just a bad pun. I was talking about how we like trivalent graphs for quantum gravity. And if you look at the x, it's kind of like a 4-point interaction term. Now, this is just a silly bad joke, but if we were to factorize that x into a 3-point interaction, what we get is the letter h. I'm not suggesting that this h has to do anything with quantum gravity at this point of that stage, but the point is we do have hn symmetries, whereas there is no xn symmetry. And we have an, dn, and en. So it actually makes more sense to look at ADEH rather than ADEX because the H has more meaning. Also, there's this playful story of factorization, and we'll see that these HN symmetry groups are coming from exceptional groups which relate to the octonions, which relate to this manifest trivalent graph structure that was conjectured previously. Now, the basic idea is that one thing you can be interested in is looking for extremes, right? You can look at, well, what is the maximal dimensions where I can have an HN symmetry? In this case, it stops at H4. There is no H5, right? Just as there's no finite dimensional E9, it stops at E8. We can project to H4 from there, but there's no E5. Similarly, when we look at hyperbolic honeycombs, there are no 6-dimensional hyperbolic honeycombs. There are only 5-dimensional hyperbolic honeycombs and lower dimensional hyperbolic honeycombs. So this is curious, as when we looked at the discrete holography picture, we understood that there was a 2-dimensional hyperbolic honeycomb that was in the bulk that had a 1-dimensional quasicrystal in the boundary. Also note that F theory embraces the 3-brane, and that 3-brane is thought to be wrapped on a 4-dimensional CFT, which has a 5-dimensional bulk that is hyperbolic. It's anti-de Sitter space. So if we were to discretize this ADS5 CFT4 holography, we would be inspired to look for some 5-dimensional hyperbolic honeycomb with some 4-dimensional quasicrystalline boundary. And curiously, independent of that fact, we know that we can't have any HN symmetry that is larger than four dimensions, and we can't have any discrete hyperbolic honeycomb that is larger than 5 dimensions. So what's telling us the limits of what is possible is really suggesting that this is where it's the simplest, where you can get these nice hyperbolic honeycombs. Honeycombs are very regular, but there's no regular structure in higher dimensions. So there's something simple that stops. And it's really remarkable to see how discretizing membranes should lead to some notion of the H4 quasicrystal on the boundary of some 5-dimensional hyperbolic honeycomb. So that's the basic idea for what we're going for. Okay, so now to provide a fresh perspective for some of the physics, this actually repeats some of the stuff I mentioned, but we'll go through it a little more carefully. One of the big problems to get 3 generations of matter is not just to get the states, but we also want mass flavor oscillations. We need to understand the dynamics of how mass and flavor eigenstates rotate between each other. Also, I want to point out that in order to get the states of the fields, we don't actually need to nail the standard model, as we know the standard model will break to SU3 cross U1. This is important for motivating the utility of spin 8, as it's well understood that spin 8 cannot lead to the standard model. It can lead to this SU3 cross U1. So the basic idea is that since we understand that spin 4, and spin 8 can lead to this, there is a hope that we can look at this duality and understand how the states of the standard model can be related to different bases stemming from the geometry of E8. So from here, we can look at spin 4, 2 and understand it as SU22. And the interesting thing about this conformal group is that we can uplift it in two different ways. One way we can uplift it is to add an additional U1, and that can uplift to spin 4, 4, or we can add a U1 in a different way to get SU32. So what we're finding is that spin 4, 4 and SU32 are two different generalizations of the conformal group that admit 3 generations in different manners. And so it looks like all this structure is suggesting some dual picture where maybe we can have one side for mass eigenstates and potentially another side for flavor eigenstates. That's the basic idea. This is still work in progress, I should mention as well, but there's what's been established is the group theoretic representation theory. We were able to establish that these paths do lead to the same point at the end. So as I was saying, if you take the 24 cell, this is the D4 root polytope. That relates to spin 8, and it also relates to spin 4, 4, which is one side of the duality that we're interested in. The basic idea is that octonionic multiplication can give spin 8, and it's understood that spin 8 can lead to SU3 cross U1 with the appropriate charges. Also, as I mentioned, spin 4, 4 can be used for double field theory to lead to a dual Lorentz symmetry. And we know that the split octonions lead to this. An important motif at QGR is to understand how the cuboctahedral symmetry are found within the 24 cell symmetry. From the perspective of the root polytopes, that corresponds to selecting a D3 inside a D4. And what you see here is actually some jewelry for a 3D rendering of the 24 cell. And what you'll notice is you can actually see a cuboctahedron encoded in the vertices of the 24 cell, which points out to the fact that D3 is inside D4. And then when you look at the Lie group interpretation and you focus on spin 4, 4, you realize that this makes contact with a couple different types of D3s. We can have spin 4, 2, which is the conformal group, and that leaves this additional U1 left behind, which in the super conformal community is called an axial U1. Also, we could look at a different type of D3 inside spin 4 associated with spin 4, 4, and that D3 would be associated with spin 3, 3, which is known to be isomorphic to SL for R. It's also known, not everyone knows this, but it is known that you can get the graviton by looking at the quotient space of SL4R with the Lorentz group. So we can get aspects of the graviton here. It's also understood that spin 1, 1 leads to dilations or scale transformations. And these are what is found in the double copy, which is related to the dual Lorentz symmetry in here of the double field theory. So we're seeing some nice structure emerging from here. So if we focus on the D3 for a moment, and we now go up to E8, and we take the root polytope, we project it D3, we're going to find this cuboctahedron right here. There's going to be a single root vector at each vertex of the cuboctahedron that is corresponding to any of these D3s that can be found in E8. We also know that there are octo-octonionic spinors stemming from the Rosenfeld plane that are inside E8. And when we break in this way, we find that the 128 spinor leads to 816 spinors, which are found on the tips of two dual tetrahedra, which make a dual, what's called a Merkaba sometimes. And so we have this fermionic Merkaba with this bosonic cuboctahedron. As we see, the other bosonic degrees of freedom are associated with the square centroids that are lying on the cuboctahedron. So if we look at spin 12-4, we can think about a couple different D3s. This is just a couple, there's others as well, but we could look at spin 3, 3 cross spin 9-1, as I previously mentioned. And this can be helpful for understanding how 3 mass generations might be encoded. Also, people have been interested in dual conformal symmetry, so it's just curious to point out that if you look at spin 4, 2, you'll have a residual spin 8, 2, and you can get 2 dual conformal symmetries. So now that we dive back, let's dive back more into the dualities stemming from E8. These dualities occur at multiple levels. We have this ADE this notion of ADE classification, and we can start in 8 dimensions. We have A8 and D8, which are both contained within E8. Then we know that we're eventually going to go to H4, and so it's instructive to think about D4 and A4. It's also worthwhile pointing out that D8 can break to D4 cross D4, while A4 cross A4 is an independent maximal subgroup of E8. So the basic idea is all 4 of these can be obtained within E8 in different ways. And when we look at the Lie group structure, we get SU72, or we can get SU32 cross SU5, or we could get SO12-4, spin 12-4, or we could get spin 4, 4 cross spin 8. And here, the basic idea is that we want to think of the A4 side to be associated with local symmetries, while the D4 symmetries are associated with global symmetries. And the idea is that the H4 symmetry is kind of neither A4 nor D4, yet has motifs that are comprised from both aspects. So we have a single quasicrystalline model that obtains gravitational aspects stemming from D4, yet also local gauge symmetry aspects of the standard model stemming from SU5 associated with A4. So as I was saying, if you just focused on the D side of things, it becomes difficult to actually get the standard model gauge symmetry. However, you can get the states, the fermionic states in the standard model. You just won't make contact with the electroweak symmetry. However, the AN side of things helps greatly with that. And what we found is, well, there is one path where you can go from SO12-4 to get to SU5 through SO10 right here. There's also this path through SU5 plus SU32, and there's also this path through SU72. All 3 of these different paths lead to the same low energy states at the representation theory level. And no one had pointed this out before, so that was our major contribution here, is to point out that this particular non-compact real form of E8 can lead to 3 charts of the conformal group with SU5 in a curious way. To dive into this a little more, what we really showed is that if you break SU32 cross SU5 down to the standard model, and then you break the standard model to the SU3 cross U1 with the electromagnetic U1 charges, we found that if we broke down to the same low energy physics on this side, here we're bypassing the standard model, and we're able to show that the representations on both sides were equivalent. This gives us hope that we can have a faithful representation from both sides of this duality and find structure for these states from both. Typically with gauge theory, you think of breaking along one chain of symmetry breaking, but here we're trying to use dualities to understand how some new type of theory can emerge that considers 2 chains of symmetry breaking instead of 1. And the basic idea is that the quasi-crystal structure is going to relate to holography. Now, when we look at holography as it's used in string theory, there's this notion of ADS5 cross S5 that's coming from 10-dimensional string theory. There's also the 11-dimensional supergravity, which allows for compactification to ADS4 cross S7. Now, neither of those can lead to the standard model, especially not 3 generations of the standard model. However, it is curious to think, well, can I get something higher? What can I get ADS5 cross S7? It's hard to imagine that because it would come from something beyond 11 dimensions. But as I was articulating, it was actually briefly shown in 1996 that there is motivation to go to 12 plus 4 dimensions or 16 dimensions rather than 11 dimensions. Now, what we found is that there's a particular generalization of ADS5 that we can refer to as AH4, 3, which is defined as the quotient space of spin 4, 4 divided out by spin 4, 3. This is like a 3-time generalization of ADS5, just as we saw that 3 time dimensions allowed for contact for 3 mass generations. We know that the isometry group of S7 is the SO8, and we articulated how the D4-A4 duality allowed for us to make contact with the standard model spectrum. The spectrum broke into low energy. We can get that in the SO8, which is related to S7. In this way, we seem to have some holographic model that can allow for 3 generations of the standard model. Another interesting observation is that, well, our universe, the physical universe, expands, and de Sitter space is useful for that. We want de Sitter space. The physical universe is de Sitter, not anti-de Sitter. However, the mathematics of anti-de Sitter is easier, so string theorists have mostly explored ADS. However, there has been some work done on de Sitter holography. There's a few observations. One observation is that ADS5 can lead to DS4 through the Randall-Sundrum model that's related to that. There's also this other observation that realized you can use two patches of ADS3 cross ADS3 to lead to DS4. Now, what we're finding here is that this AH43 allows for two notions of ADS3 cross ADS3, which allows for the uplift back to DS4. However, if we just break AH43 directly to DS4, we find this new internal S2, which is associated to mass flavor oscillations. This helps clarify the role of the three time dimensions from the gauge theory standpoint, as at first, it seems bizarre to have a theory with multiple time dimensions. But now it's more clear that we have a single DS4 with additional time-like dimensions that are simply associated with mass flavor eigenstates. So we can have a rotation of some internal sphere with a single space-time that is encoding these states. Now, if we want to get into using ADS, such as ADS5, we could break to different ADS5s and get S1s and use that to potentially make contact with DS4, or we could use these ADS3 cross ADS3s and potentially uplift them, or we could just go directly to DS4. So there's a lot of new holographic models that can be explored from here. And I want to also point out that there was a remarkable result from Witten where he looked at spinors of spin 2, 2 and found remarkable results related to classical scattering for QCD recursion related from these spinors. So it's really beautiful to see how the mathematics is encoded here, but also there's a lot of rich physics here as well. So now to try to motivate the quasicrystalline perspective, we're going to want to think about a few geometric aspects. So before I discussed the 5-4 hyperbolic tiling, and what we found is that 5 physical qubits led to a single emergent logical qubit. We found that the 1D Fibonacci chain was encoded on the boundary of this 2D hyperbolic tiling. The conjecture here is that some 5-orthoplex hyperbolic honeycomb in 5 dimensions might actually relate to Elser-Sloan quasicrystal boundary. If that were true, then this would give us some new discretized ADS-CFT correspondence. And this would be related to the structure of identifying H4 from E8. Now, when you go through the Elser-Sloan projection, what you'll find is that you'll get this 600 cell that has H4 symmetry. That is like a generalization of a dodecahedron. Now, what is understood is that this 600 cell actually has 5 24 cells that can be fit inside that. And here I have a picture of a 24 cell rendered in 3D and then a 600 cell rendered in 3D. Just to depict this concept of having a 5-fold compound of one polytope and another, it's helpful to think of 5 tetrahedra that are compounded such that you get a dodecahedron here. The basic idea is that the 600 cell vertices in the Elser-Sloan quasicrystal can be interpreted in 2 ways. One is to think of them as a single 600 cell. Another is to think of them as 5 24 cells. At first glance, it's most natural to think of the 600 cell, since that is the natural polytope associated with the H4 symmetry. However, we know that D4 is associated with the 24 cells, and we understand that the isometry group of the holographic brain worlds that we're finding motivates utility of a 24 cell. And we also saw that this notion that we needed a minimal of 5 number of qubits to be entangled to lead to error correction. We also know that E8 leads to error correcting codes. Therefore, it seems well motivated to search for the idea that we could have some pseudo twistors stemming from spinors of spin 4, 4, and looking at 5 entangled pseudo twistors that are geometrically realized as some 600 cell. As such, we'll realize that the 600 cell may one day encode 5 pseudo twistors such that an emergent pseudo twistor can emerge logically, just as it did with what we found with these two-dimensional hyperbolic tilings. From here, you would hope that the inflation symmetry of the quasicrystal allows for a new method to allow for renormalization of spacetime. This is a problem with discrete lattices because a lattice always has a fixed scale. But we know that quasicrystals have an inflation symmetry, which changes the scale. So this is another reason to motivate why we would hope that quasicrystals would provide additional value that discrete lattices could not provide for the study of quantum gravity. To dive into more of the geometry of what QGR is interested in, we had the story of taking a cuboctahedron inside a 24 cell. One way to think about this is to identify 12 vertices of the cuboctahedron. And when you look at the group theory of breaking spin 4, 4 to, let's say, spin 4, 2 cross spin 2, what you'll realize is that spin 4, 2 has 12 roots associated with the vertices of the cuboctahedron, but all of the singlets with respect to that go to the origin, which is a point. That gives us 13 points. Those 13 points are visualized right here as 4 tetrahedra. These tetrahedra are arranged in such a way that there's cuboctahedral symmetry, but there's this additional point at the center. What QGR is interested in is finding 5-fold compounds to lead to H3 symmetric quasicrystals. What you can find is if you take 5 of these 4 groups of tetrahedra, and you compound them in the appropriate way, then you can obtain this 20 group. What's also remarkable is that we found that really Fong and Clee Irwin, they found that there is this Fibonacci icosa grid that leads to a 3-dimensional quasicrystal that contains 20 groups. And currently our group is investigating how this quasicrystal is related to the structure of E8. One of the reasons why we're interested in focusing on the 4 group is so we can get to different notions of binary combinations that are reminiscent of what we're used to with bits and qubits. So we have spin states, spin up and down. And we notice that when you take a cuboctahedron, you can actually get a 4 group of an up and down orientation. When you take a 5-fold compound of the up orientation, you get a 20 group that is twisted one way. And if you take a 5-fold compound of the 4 group oriented in the other way, you get a 20 group that is twisted the other way. Just as a cuboctahedron can be separated into 2 4 groups with different binary up and down orientation, we find that the 20 group itself has 2 twisted orientations of left and right twist. Another way I should mention to visualize what the 20 group is to instead start with an icosahedron, but instead of taking an icosahedron, try to take 20 regular tetrahedra and try to make an icosahedron. What you'll find is that you can't form a perfect icosahedron, there will be gaps, but you can twist it either left or right, and this is a type of defect. So we can find that the 20 group is encoding a defect, which is related to defects in condensed matter, which actually relates to gravity in some sense through the metric affine gravity. But I'm not going to go into those details, but the basic idea is that the twist, the left or right twist, is a particular type of defect that encodes a generalization of, let's say, curvature or some gravitational field strength that we're currently investigating. And the idea is that we can get aspects of spin that might be related to these notions of twist left and right. This would allow us to get to notions of quantum computation as we would have access to some binary choice. I also wanted to highlight some work that is primarily led by Marcelo Amaral here at Quantum Gravity Research. And what he's been doing is looking into the structure of quasicrystals and trying to understand how state sum formulations stemming from loop quantum gravity can be utilized to motivate an understanding of how to get some state sum formulation of quasicrystals. So here's just a depiction of the cut and project methods going from a 2D Z2 lattice to getting a Fibonacci chain. And this is just a simplification of what you can do. You can also get the Penrose tiling from Z5. You can also get other quasicrystals from A4, D6, and E8, as we mentioned. And so Some of our collaborators have found some additional works showing that geometric state sum models can be found for quasicrystals. This also helps point out the possibility of finding emergent spacetime from quasicrystals. I also want to mention this notion of nested Hopf vibrations. There are these notion of Hopf vibrations, so you can have, basically the idea is you have some principal bundle, and then there's some base manifold with some fibers. So the maximal Hopf vibration is this S15. You can imagine a sphere in 16 dimensions, and it turns out you can find multiple S7 spheres on that S15 that are non-intersecting. And when you go through this, you realize that you can represent those as fibers, what are called fibers. And when you look at the structure, you realize you can get this S8 as a base manifold. And these Hopf vibrations are all related to projective lines over the division algebras. And similar to how the real numbers are found in the complex are found in the quaternions, and the quaternions are found in the octonions, turns out that you can nest these Hopf vibrations. Another curious fact is to point out that there are discrete Hopf vibrations as well. The Gaussian polytope is the E8 root polytope, and that is a discretized S7 with 240 vertices. The submaximal discrete Hopf vibration of S7 to S4 base with S3 fibers, when you discretize this, what you find is you'll get 10 24 cell fibers, and you'll have a 5 orthoplex base manifold. What is really curious about all this structure is that this discrete Hopf vibration has 24 cells in a way that mimics the structure of the projection of the Elser-Sloan quasicrystal. If you looked at this 5 orthoplex and you focused on the northern hemisphere of this 5 sphere that is discretized, you would find 5 vertices where each vertex corresponds to a 24 cell. So the northern hemisphere of this discretized 5 sphere would have 5 24 cells. And Ray Aschheim here at Quantum Gravity Research was able to understand how you can rotate between these fibers back on the Gaussian polytope, which corresponds to precisely the 5 24 cells that are contained in the 600 cell in the Elser-Sloan quasicrystal. Therefore, it is suggestive that this discrete Hopf vibration has information that is related to aspects of the quasicrystal. And it's also understood in the literature that Hopf vibrations can lead to novel manifolds that allow for nice formulations of spacetime. I'll also point out that we can get a generalized Hopf vibration for this particular non-compact real form of E8. There is this general Hopf map that I was able to find. I should say that this hasn't been proven. I haven't proven yet that is a valid vibration, but the basic idea is that there are 2 Hopf vibrations that do exist and 3 real forms of E8. Those 3 real forms of E8 contain various non-compact and compact realizations of SO16, which is the symmetry of the maximal Hopf vibration. Currently in the literature, 2 of those bosonic sectors of E8 have Hopf maps, so we can construct a 3rd Hopf map for the phenomenology that we're interested in and explore in future work to identify if this Hopf map leads to a valid Hopf vibration such that we can get a new generalized Hopf vibration for an implementation of these holographic spinors so we can encode the 3 generations of matter with the standard model as I suggested. And just to iterate a little more details, when we uplift the 4 dimensions of space-time to 3 dimensions, we can think of that 2-dimensional sphere of rotations to be time-like rotations to encode mass flavor oscillations, as I was briefly mentioning. Okay, so now with this information about the discrete Hopf vibration, it motivates a further, this is actually coming from Cleoran. What he realized is what we can do is go back to E8 and look at, instead of the Gaussian polytope, let's look at what we call the 24 cell 10 compound. Rather than thinking of the Gaussian, we think of 240 vertices that are associated to these 1024 cells. If we think of the Gaussian polytope and replace the Gaussian with this 24 cell 10 compound, as we follow through with the quasicrystalline projection, we can get aspects of the discrete hot vibration and understand how that leads into the quasicrystal. From there, there's a few different ways we've been currently just exploring getting three-dimensional quasicrystals. Actually, at the time that I made this presentation, one of the main things we've been interested in is taking three-dimensional slices of the Elster Sloan and compounding them. That leads to what we've been calling the compounded quasicrystal in 3 dimensions, which has 20 groups that are similar to Fig. And recently, we've actually realized that there's another process where we can directly go from E8 to 3D and get quasicrystal that has H3 symmetry that is similar to this construction that I'm describing here. And what's remarkable is that Ray was able to confirm that there is this 5th roots of unity 8x8 matrix that rotates between 5 pairs of 24 cells in 8D, which maps between the 24 cell fibers in the discrete hot vibration, yet also describes how we can decompose the 600 cell into 524 cells, as I was mentioning. To get back to connecting all of this to string theory, I figured I'd go through the evolution of string theory. Well, really, we started with this idea that there was 0-dimensional particles in 4 dimensions, and then it was realized that you can have strings in 10 dimensions, and these strings are 1-dimensional rather than 0-dimensional points. From here, what we found is that Witten introduced M theory, which embraced these 2-dimensional membranes in 11 dimensions. And the 11 dimensions was also studied previously in supergravity. From here, you can imagine going further to 12 dimensions, such as F theory, 13 dimensions, which was introduced by Isaac Bars and called it S theory, while Vafa introduced F theory. And finally, there's this newly conjectured A theory in 14 dimensions, stemming from work of Bars and Seskin in 1997, that was never followed up until recently. And so you can ask yourself, okay, what are these strings? What are these 2 branes? What are these 3 branes? I mean, they're just extended objects with material-like properties. And so we have this 3 brane, and really what it is you have this vacuum, and then there's this extended object that is filling up 3 dimensions of space, and it has properties. That is basically calling it a material. It's basically an ether, but obviously we don't want to say that. But since I was giving this talk to Louis Kauffman, I figured I'd point out that Peter Tate introduced knot theory with Kelvin in order to attempt to describe the ether. And Louis Kauffman is a pioneer of knot theory. Also, at UCLA, Robert Finkelstein introduced this Q-deformed SL2Q and introduced this trefoil knot to make contact with the standard model. And what's remarkable about this is he was able to unify QCD with Schwinger's theory of the strong force that didn't use SU3 and used this notion of dyons via these topological dyons. And so what Finkelstein was able to realize is that this preonic model of topological dyons allowed for a unification of QCD with Schwinger's model. And it's also pointing out that while Finkelstein's work is not well cited, he was able to convince Sergio Ferrara that supergravity is a gauge theory of gravity. So there are some experts that do listen to his opinion. However, no one, for the most part, very few people have cited Finkelstein's work on this knot theory model of the ether. I shouldn't say ether, maybe more like flux tubes or strings, right? And so in this paper by Finkelstein, what he finds is he gets these trefoil knot, and the crossing of the knots correspond to the preons, and then the whole knot itself, depending on its structure, leads to the charges associated with neutrinos, charged leptons, and up and down quarks. So going back to string theory, let's forget about the ether. We have these 3 branes, and what was actually shown is that the true origin of this 3 brane is stemming from 14 dimensions. This was worked on briefly around 97, but then similar to the work of Martinek, it was kind of left as everyone has been more recently focusing on M theory and F theory. People haven't really explored S theory, or this this A theory wasn't even coined back then, so no one has even explored this yet besides some of our collaborators. And the basic idea is that this 3 brane is some volume of some spatial material embedded in these extra dimensions. And so what is the motivation of these extra dimensions? The basic idea is that we want to unify charge and momentum. We want to have some extra dimensional conservation law. We know that space-time symmetries lead to energy and momentum conservation, and we know that there's charge conservation, which implies gauge symmetries. So when we unify the gauge symmetries with the space-time symmetries, this is a natural motivation for extra dimensions. So these extra dimensions are simply internal dimensions for understanding charge conservation. So now, if we're going to work towards some unified field theory, it's worthwhile to point out that there's this superalgebra, and D equals 11 plus 3 dimensions. And this superalgebra truly unifies all of the superalgebras of all of the supergravities and all of the supergravities. This is something that M theory and F theory does not do. M theory must resort to dualities to understand how to make contact to all of the different string theories, as it is stated that M theory unified all the string theories. But it only did so by going to lower dimensions, which really suggests that M theory is not the final story. As we see, people have moved on to F theory, which embraced the 3-brane, but it doesn't completely unify all the superalgebras. Bars and Seskin pointed out how this works at the superalgebra level for mathematics, but all of the physicists, for the most part, were scared of the extra time dimensions, which we now understand relate to 3 mass generations. So now the physical interpretation is more clear, and we can proceed forward with generalizing M theory and F theory to get the appropriate phenomenology. As we were describing, this E8 minus 24 relates to a background independent notion of 2-time M theory, and E8 minus 24 was also studied by Lisi in 2015, but he had some details of his model was not complete. So what Mike Rios essentially realized was that Garrett-Lisi's model can be made rigorous by unifying it with a generalization of M theory, which he dubbed as A theory. And he found these papers and realized that there's this 3-brane that has an S-dual S-brane, which generalizes the 2-brane and 5-brane that are S-dual in M theory. Furthermore, if we uplift to 12 plus 4, which is the conformal group of 11 plus 3, we get a 4-brane and an S-dual 8-brane. Okay, so what is A theory then? I gave a talk to a public audience where I took this slide from, and let's just say you only knew how to count to 14, right? So, okay, what is A theory? It's this 14-dimensional theory that has 11 space dimensions and 3 time dimensions. But how can we think of these spatial dimensions? As I was saying, we can realize that charge and momentum can get unified together. So really, these extra spatial dimensions are gauge-like dimensions. They're really associated with the charge identities of these particles, but there's some internal space. And so that gets unified with space to give these 11-dimensional space dimensions, and then we have 3 time dimensions. But really, we know that there's only one causal timeline for our reality. Each observer experiences one flow of time. So what could the other 2 time dimensions be? Well, they're actually rotation angles that are changing the internal state, the internal identity of the particle that is evolving. As such, we can get these 3 generations associated with these 3 time dimensions, and then these 8 charge configurations correspond to a single electron, the 3 colored down quarks, the 3 colored up quarks, and a single neutrino. If we multiply this 3 and 8 together, this gives us 3 generations of the standard model. And this is stemming from the structure of this 4-dimensional theory. So as we see here, we're using some generalization of M theory, but I can very simply explain to you why this leads to the standard model. This is something that becomes a little more challenging with M theory. And when we look at the quantum phase space, we see that momentum is conjugate to space and energy mass is conjugate to time. Similarly, this charge is conjugate to gauge freedom. Another way to think about these extra time dimensions is to really think of them as energy dimensions. And we know that since E equals mc squared, energy is like mass. So if instead of thinking of as generalizing space-time, maybe you could go to energy momentum space and generalize the energy momentum space to have 3 energy dimensions, or 3 mass dimensions for 3 mass generations. So as I was saying, you can break down the 14 dimensions in this way. And with these 8 different charge configurations and these 3 different masses, this gives 8 times 3 equals 24 different matter particles. Now, when we're thinking about how many different masses there are in the Standard Model, we want to understand that even though there's 3 quarks with different color, the red, green, and blue quarks all have the same mass. So when we have 3 quarks and 1 lepton, we have 4 matter particles, but that only leads to 2 mass values. So out of all of these 24 matter particles, there's 12 unique masses stemming from this A theory. So we could ask ourselves, can we go beyond A theory? How could we do that? This is really hilarious because it combines insights between Gerrit Lisi, Eric Weinstein, and really inspiration from string theory, even though it currently appears to the public audience that all of these people are in competition. What actually happened was Gerrit Lisi mentioned this E8-24 at a conference around 2015, and Eric Weinstein was attending that conference. He mentioned this notion of weak triality in 24 dimensions, and Mike Rios thought that this weak triality must be related to his theory of geometric unity that was so mysterious. So Mike Rios was inspired to think about how can we generalize E8 to find some algebra that has this notion of weak triality. And what we found was this infinite class of finite dimensional vertex operators, algebras. They're not Lie algebras, but they do contain the exceptional Lie algebras. And they do create an infinite class of finite dimensional algebras that contain the exceptional Lie algebras. And they admit a notion of Bott periodicity in their structure, which relates to an 8-fold periodicity associated with the symmetry of spheres. So the symmetry of the spheres relates to orthogonal rotations of vectors, but we also have fermions that are in spinor representations, and we want to use these exceptional groups, or maybe superalgebras derived from these exceptional groups that encode fermionic states. So Bott periodicity is nice, but it's missing the spinors. And the basic idea is that these magic star algebras of exceptional periodicity allow for a unification of Bott periodicity with spinors. So this leads to a new infinite class of superalgebras that we were able to find and get published. And it is understood that as soon as you have these superalgebras, that instantly, since they're vertex operator algebras, that instantly implies a new CFT. So we essentially found a new infinite class of theories, although we did not articulate the precise structure of those theories and focused on the mathematics. So here, as you can see, we discuss all of these different ADS7, ADS4, and we have these S8n for integer n, and we can go up to infinite dimensions. So now we can allow for infinite dimensional extensions of M theory and A theory that allow for Bott periodicity. So we can go to 12 plus 4, and then we can go to 20 plus 4, and then we can go even further to 28 plus 4. And once we're at 28 plus 4, we could remove 2 time dimensions there and get something like 28 plus 2 dimensions. And so these are some wild symmetries. And so we get these E8n algebras that generalize E8. And there would then be non-compact real forms of these EP algebras, such as E8-3. So if you went to some high E8n of these EP algebras, you could get E8-4, and there would be different real forms of that. And it's curious to note that there's all this various different structure. You can get contact to all these different subgroups. And I just pointed out how the standard model fits in here. You can get to SO5, fit that in SO10. We talked about how that can lead to E6. This can fit in SO18, but it's also curious to point out that E6-2, this new algebra, contains SO18 with some additional spinors, but there's also this E8. And there's also all these other algebras as well. So now when we're going beyond E8 and thinking about 24 dimensions, this makes contact with the Leech lattice in the monster group. And it's worth pointing out some meaning for the physics of the monster. You could ask, what is the meaning of the monster group? John Conway said that there's never been any kind of explanation of why it's there, and it's obviously not there just by coincidence. It's got too many intriguing properties for it to all just be an accident, right? And Freeman Dyson, on the other hand, said, we have strong evidence that the creator of the universe loves symmetry. And if he loves symmetry, what lovelier symmetry could he find than the symmetry of the monster? So the basic idea is we don't understand why the monster group exists mathematically, yet we know the universe likes symmetry. So maybe there's some physical motivation for why this thing could exist, or maybe there's some physical theory that uses this mathematics. And what we're able to find is that, well, the Grease algebra is the minimal representation that the monster group can act on, and you can decompose this Grease algebra in the following way. When you get this 98,280 degrees of freedom, you actually find that this is 1/2 the degrees of freedom of the Leech lattice itself, because if you have 98,280 plus 98,280, you get the 196,560 associated with the Leech lattice. And there's this notion of dual branes that we were discussing before, and we go to higher dimensions, we can get this 5 brane and some 23 brane. And so if we select the 5 brane at world volume, stemming from the Leech lattice, that is giving some Z2 orbifold of the Leech lattice, and then giving us the 98,280 that corresponds to what is found in the Grease algebra. However, there's also this mysterious 98,304 that Conway found, but he didn't understand why this number was here. And one answer to why this is here from a physical perspective is to support supersymmetry in D equals 25 plus 1 and 26 plus 1. There are string theories in these dimensions, but they typically don't have supersymmetry. Finally, it's worth pointing out that this representation right here, if you just think about what would a gravitino in 27 dimensions be, it would correspond to this spinor. It would correspond to this representation. And we can break this representation into 26 dimensions and break this 5 form down to 26 dimensions. And then we realize what's left over here actually corresponds to the graviton and the dilaton in 26 dimensions. So we get the graviton, the dilaton, and the gravitino, and some additional higher P forms. And previously, it wasn't understood why or how you could have supersymmetry in higher dimensions, because they understood that the spinor was so large and this is so small. No one had really thought to go to even higher dimensions to find some origin that allows you to get similar counting of degrees of freedom that at least gives you some bosons that is similar to the number of fermions right here. So the basic idea is that we can uplift to this SO28, 2, and think of that as the one-time conformal symmetry group from this SO28, 4, which can be thought of as the quasi-conformal symmetry of SO25, 1, which is typically associated with bosonic string theory. It's a bit of a mouthful to take in, I agree. But the basic idea is these EP algebras gave us contact to this notion of SO28, 4. And there's also a relationship to the spinor to this story as well, but I won't go into that detail. So now, if you look at these P forms, they're related to Clifford algebras, they're related to membranes, and they're related to Pascal's triangles. So we see if we look at Pascal's triangle, maybe you've seen the 1 going to 1, 1, 1, 2, 1, 1, 3, 3, 1. But let's just keep going. Let's go down here. Once you get down here, you can identify you get 98,280. And it was funny, Clearman actually inspired Mike Rios to notice this based on the structure of E8. And he realized that if you break this down, you get all these P forms that can be found in lower dimensions. Also, it's worth noting that you can get, basically the idea is if you go to 25 plus 1 dimensions, it's understood that a super Yang-Mills theory should double copy to lead to some supergravity. That relates to finding gravity via the double copy, as I was talking before, from Yang-Mills theory. And the suggested n equals 1 super Yang-Mills multiplet involves this weak triality that Eric Weinstein mentioned, which actually has nothing to do with geometric unity. So ironically, Eric Weinstein, in his attempt to go away from string theory, actually helped us understand how to find supersymmetry in higher dimensions. This weak triality suggests that you could have a 24 vector, but then this 3 form, such that you get 248 bosons and 248 fermions. Now, when you apply this double copy, you expect to get this huge number of off-shell degrees of freedom. But then when you think about the on-shell degrees of freedom, you end up getting this 196,608. And this is what we discussed in this, this paper on the archive here that we put out a year and a half ago. So what's curious about this 196,608 is it's right in between the 196,560, which corresponds to the Leech, and the 196,884, which corresponds to the Greece. So it's curious to understand why all these numbers are close, but not exactly the same. And the quick and dirty answer is that there are these network of other weak trialities that allow for coincidences that allow you to switch certain types of degrees of freedom for others. For instance, you can take this 300 P form and break it to 276 plus a 24, but you also realize that this 300 is equal to 299 plus 1. This is a type of weak triality. It's not exactly like triality, but it's similar to that idea of triality of SO8 and this weak triality that Eric Weinstein pointed out to us. And so this turns out to be related in kind of a complicated way to how you can get these types, the Leech lattice and the Grease algebra, to lead to some multiplet. The basic idea is you take that P form from 28 plus 2 dimensions, you break it down, and you use this weak triality to recover a graviton from some of the P forms. You remove some of the P forms to obtain the graviton, and then you can remove some other degrees of freedom such that you can get an equal number of bosons and fermions. And what's remarkable is that the mathematics of the construction helps point out which degrees of freedom should be removed. So there's a lot of self-consistency between the whole thing. This relates to the story of bosonic M theory that was introduced by Susskind and Horowitz as well. And so we're claiming that we made contact with this and can basically add fermions to bosonic M theory. And this also makes contact to Witten's notion of monstrous CFT, which uses SO24, is related to the Leech lattice, but no one had connected how bosonic M theory in this, well, maybe there is some work discussing the relationship here, but we're at least able to understand this from a new perspective as well. So now we're basically conjecturing that there should be supersymmetry, a supergravity theory, in D equals 26 plus 1 dimensions as a Bott periodicity extension of D equals 10 plus 1 supergravity, N equals 1 supersymmetry. When you look at the P forms of this theory, you can break it down in this way, and you can eventually write down this Lagrangian. And so you could ask yourself, well, what is the utility of such a theory? As we were briefly describing before, E8 already described the standard model, and these new superalgebras give us additional fermions, additional matter particles. So wouldn't it be marvelous if the Leech, the Grease, and the monster are hiding the dark matter, right? Maybe there's more matter than the visible matter, and this monstrous A theory is suggesting us a way to recover some dark matter multiplet. So we were able to write down this Lagrangian that is a candidate for a supergravity theory. We weren't able to yet prove the supersymmetry because in order to do that, we would need to solve about 6,000 coefficients. So we haven't gotten around to solving those coefficients yet in order to prove that the theory is supersymmetric with the appropriate choice of coefficients. However, it is anticipated that such a theory should be supersymmetric. Regardless of that, it's still a rich and interesting theory within its own right. So this is the abstract of the paper that is discussing this work. So to discuss another paper that we were able to collaborate on, we were able to understand how brain-world intersections stemming from these higher dimensional theories could actually pinpoint the standard model and then also get this dark matter sector. You know, what actually happened was when we were at QGR, we were discussing with a dark matter researcher, and she suggested that her analysis found that we need around 2,000 degrees of freedom. And we had these new algebras that gave 2,048 degrees of freedom. So the natural question is 2,048 close enough to 2,000? She said yes. She wasn't sure exactly how many degrees of freedom there were, as that related to the mass of the dark matter. And so we can have different masses of the dark matter, which would relate to a different number of degrees of freedom based on her model for warm dark matter. So this motivated the search. When we looked into the structure of the superalgebras, we were surprised to find that the structure of all of the branes in the superalgebra suggested this nested structure such that there was this 11 brane world volume that encoded the standard model, and that related to the 11 dimensions of A theory, the 11 plus 3 the 11 spatial dimensions of the 11 plus 3 theory. The 3 brain from there isolates spacetime, and this dual 7 brain encodes aspects of the charges. However, there's this other 19 brain that shares the same spacetime, but has a different charge sector that is larger and has the 15 brain. This is where the 2048 spinor comes in, while the 128 spinor comes in here. And so what we found is that there's this 23 brain that is dual to the spacetime in this larger theory that contains both the matter, the standard, the visible matter and the dark matter. And the entire theory altogether is this 27-dimensional world volume that contains all of it together with space itself. So what we were able to understand is that the mathematics of the superalgebra indeed led to a derivation of intersecting brane worlds that picked out 128 and a 2048 spinor, which independent analysis suggested that the number of independent degrees of freedom for dark matter, according to this warm dark matter model stemming from Cinziana, should lead to roughly 2048 degrees of freedom. So that was quite a remarkable surprise to us to find. Another curious point is that Weinstein has his theory of dark matter, and he uses this group U64, 64. Remarkably, while he doesn't use any notion of 27 plus 3 dimensions, if you actually look at the spinor in 27 plus 3 dimensions, it has the same exact number of dimensions as Weinstein's dark matter group. So in a way, what we ended up finding was much different than Weinstein's theory, but there are some mathematical motifs that have vague similarity. However, this model is much closer to a generalization of M theory and string theory rather than being some competitor. So with that being said, I'll conclude by saying we introduced this notion of 5-fold tensor networks, which allow for quantum error correction. We looked at quasicrystals and saw how they had 5-fold symmetry and emit conformal holograms. And then we looked at these notions of phenomenology to make contact with the standard model and gravity, and we saw how they related to notions, potential notions of holographic pseudo-twistors that may stem from this non-compact real form of E8, which is suggestive that there might be some quasicrystalline spin or quasicrystalline spinor network that leads to a theory of quantum gravity that is literally an error-correcting code. So the basic idea is we'll be realizing Cleo Irwin's vision of trying to understand how to build a quantum computer by understanding how the universe itself is a quantum computer that has this pre-physical space-time code. And the idea is this pre-physical space-time code leads to an emergent logical code that has error protection through the quantum topological structure. We then finally concluded by introducing notions of monstrous M theory and monstrous A theory, and shared work on how the Leech lattice may be related to dark matter. As you may understand, there's a lot of rich and unexplored quantum topological structure that can be looked into forward. So I look forward to hearing from anyone. If any experts in any different areas are interested in any of these topics, feel free to reach out with us to see if there's any overlap between our work. So I really appreciate everyone for sticking with me and listening to this talk, and thank you very much.